what topics you'd like to have featured next, and we don't actually have anybody lined up for October or November. We are going to get a Jarle the Giant Scientist, who's like a 6'7" guy from Norway who got a PhD in chemistry here. He's a brewer. He's going to come talk to us about the chemistry of brewing beer. Should be real interesting. And we may actually have an after party with his craft brew featured. That's what we would like to have happen next. And we'll probably do more talks on machine learning and neuroscience. And I think around December I'm going to do a talk on evolutionary psychology and some of the latest results from paleontology and work on human origins, which I think I'll probably do once a year. I did it last December. It was a good time. Today I'm pleased to announce we have Dr. Luc Langston here. Luc graduated with a Bachelor's of Science in Astrophysics and Chemical Physics from Rice University, 2005, and went on to graduate school at the University of Virginia and obtained a PhD in Theoretical Condensed Matter Physics in 2011 with a dissertation titled Field Theoretical Investigation of Fluctuation-Induced Phenomena, the flux capacitor.
Yeah.
He studied formal divergences in the Casimir effect and phase transitions in condensed matter systems. And after obtaining his doctorate, Luc Langston conducted research as a postdoctoral research associate in the field of quantum computation at the University of Wisconsin in Madison from 2011-2014, and studied quantum and thermal noise as a source of qubit decoherence in semiconductor quantum computational devices. We'd love to actually have a talk getting deep into quantum computation. I think there's quite a few of us who are interested in this. So, Dr. Langston, everybody.
Thanks for coming. Also, I work here at a patent firm, by the way, so I'm no longer in academics, but was in it for quite a while. I just thought this comic was funny. Kind of cute. In any case, we will get down to business. So, thanks for coming. My name is Luc Langston. I'm going to be talking to you all today about Schrodinger's equation and quantum mechanics. So as I mentioned in the abstract, anybody read it? So my goals here are ambitious. I'm going to try to explain as much as I can the essential features of quantum mechanics without too much mathematical jargon and without requiring too much mathematical expertise. And quantum physics is, typically not something that you get into until your third full year in college if you're a physics major. So you're in your third year of taking physics classes every year, and you get to this. And the reason being that there's a lot of prerequisite mathematics that are required to work in the field. Typically, you want to have a couple years of calculus behind you, and also a good understanding of linear algebra are the main things that you need to know. So typically, it's not really accessible to the lay public. So I realize this is an ambitious undertaking, and we will see at the end of this how successful I have been. So, and of course, please ask questions along the way. Before I get started, I did want to poll the audience a little bit to see sort of where everybody is. How many of you guys have taken a college or higher level quantum mechanics course? Okay, good. How many of y'all have taken at least a semester of college level calculus? Okay, great. That's actually perfect. So how many of y'all have no idea about calculus or quantum mechanics? Okay, well we won't leave you behind, but. There's not going to be a lot of calculus in this talk. As you can see from Schrodinger's equation, there's already a derivative up there. And I thought about it, and I decided that it would be cumbersomely difficult to try to do this without any calculus. So there are derivatives and integrals, but I'll try to explain what they're doing when they come up, and it won't be too crazy, hopefully. So this is Schrodinger's equation. There's a lot going on. It's describing the wave function. And what we're going to do is break it down into its simplest components and try to start with that and explain what that's doing and how that works, and then build it up from there until we get back to the full equation itself. My talk's divided roughly into two parts. The first half is going to be doing this, sort of deconstructing the Schrodinger's equation and explaining how it works. And then the second half, which is not quite a full half because this first half is a little bit long, I'll get into some of the interpretations and questions of what this sort of means in a philosophical sense, quantum mechanics, that is. So before I get into this, I want to start kind of setting the context. So Quantum mechanics is typically discussed in contrast to classical mechanics. So I want to talk a little bit about what that is and what their relationship is. So classical mechanics is what you intuitively think of usually if you aren't really familiar with physics. This is just sort of the first thing that you hear about. It deals with fairly intuitive concepts such as positions of particles that run into each other and have different velocities, and they act on each other with forces. And it's a clockwork description, meaning that if you have a full understanding of where everything is in the classical mechanical description, and you know where everything is going, and you know how they interact with one another, then in theory at least, you should be able to, with that knowledge of the present, predict what the state of the system will be at any point in the future. So it's a deterministic model. And likewise, if you run the clock backwards, you can tell what the state of the system was at any point in the past with knowledge of the present. So this is what basically all the physics was before the 20th century came around. At least it all spawned from this basic concept that you can look at the world in terms of these different objects and particles that are all moving in different directions, and if just with adequate knowledge of where they are and what they're doing, you can tell how they're going to behave in the future. However, in the early 20th century, a number of physicists discovered that when you get to very small length scales, so around the scale of atoms and some molecules, you start to see that nature behaves in a very dramatically different way. There's just a new set of physical laws that take over, if you will, when you get to very small objects, and that was deemed quantum mechanics. And there's a few aspects of quantum physics that troubled physicists at the time. One of the biggest ones probably is that the determinism that was present in classical mechanics breaks down, meaning that if you have the fullest possible description of the current state of the system in a quantum mechanical sense, the best that you can do as far as predicting the future is you can predict the probability of a certain outcome. So the ability to predict exactly what will happen is no longer possible. In some cases it can be, but in general, knowledge of the current state of the system allows you to predict the probability of getting some particular experimental outcome, not necessarily what will actually happen. And so that was a bit of a blow to the ambitions of a budding physicist, right? So we want to explain things as well as we can, and knowing that, finding out that the best you can do is say, oh, well, this is going to happen with 50% chance. It's not quite as strong of a statement as saying what's actually going to happen. That being said, for all anyone has been able to tell, and the best that anyone, it's been verified over and over again that this is actually a fundamental feature of quantum mechanics. It's not that we just didn't do something right or that we're missing something. This fundamental uncertainty does indeed seem to be a fundamental uncertainty in the universe, for at least as far as anyone's been able to tell. One other thing about this I want to say before I go on. So I mentioned that quantum mechanics becomes apparent when you look at really, really small things. There's another way to get to quantum effects, and that occurs when you cool things down very cold to pretty close to absolute zero. So if you think about any physical object, like say this laser pointer, of course it's composed of a bunch of atoms and molecules. And if you looked at it microscopically, you'd see that all the atoms and the molecules are all vibrating around, and they're jiggling because they're at a temperature. They're at some finite temperature, room temperature, roughly. Excuse me. So it's a solid, meaning that the particles are not drifting around. They're locked in place. However, around their equilibrium, they are able to jiggle and vibrate. And if you raise the temperature of an object, they will jiggle and vibrate more vigorously. And if you heat up, say, a nail hot enough, then it'll start to glow, which means that the atoms and the molecules are vibrating so vigorously that they're able to excite the electrons away from their nuclei, and then hence it glows. So the point of all this is that all matter at any finite temperature has thermal fluctuations that are present. And when you, so everything has thermal fluctuations. Everything in the universe is composed of quantum particles. All particles are quantum mechanical if you look at them individually. And as we'll find out later, quantum mechanics describes nature as using the wave function, which was the variable that's in Schrodinger's equation. So it describes everything in terms of waves, which also have fluctuations. They vibrate. They're waves that, not like waves in the water, it's a different kind of wave that we'll get into, but there are waves that are fluctuating, and that has associated energy with it. And so it turns out that one other way to get from a regime wherein, looking at this laser pointer, it's pretty well described by classical mechanics. If you throw it, it'll go the way that you say it goes. But as you cool things down, you have a transition wherein, as you cool things down, the jiggling of the thermal fluctuations slows down. And there's a point wherein that jiggling no longer dominates over the quantum fluctuations, and you'll thereby be able to have quantum effects become apparent at a larger macroscopic scale, if you cool them down cold enough. What that temperature is varies depending on your material, but then the easiest, maybe an easy example to explain is superconductors. So there's of course a big field in superconductivity, and the really neat thing about it is that it's a macroscopic coherent quantum state, so that you do have macroscopic quantum effects that exist by cooling it down, so that the quantum fluctuations are no longer dominated by these thermal fluctuations that sort of wash out whatever quantum effects you might hope to observe. And that'll become important later in the talk. So I'll get back to that point.
Dr. Langston,
Yes, sir.
when you say that the quantum effects will become apparent in a macroscopic scale, for instance, in the superconductor, how would that be apparent to us? Like, what would we see at a macroscopic scale?
It's a great question. So one good example is that they have infinite conductivity. So if you have a superconductor, it's a single coherent quantum state, so that the particles in the superconductor are able to move by quantum teleportation, so that they don't have the friction that results from physically moving. Instead they're tunneling in a sense, and so that you can have zero resistance in these materials, which is why they're called superconductors. They conduct very well. So for example, if you get a current going in a superconductor and keep it in the superconducting state, it'll maintain that current perpetually for all of time without any loss of heat through resistance, because they aren't moving in a thermal fashion. They're moving through quantum mechanics. Okay, so getting back to Schrodinger's equation. First I want to talk a little bit about the wave function, which is the workhorse of quantum physics. So the wave function is, I need to have a little bit of a mathematical detour here. It's what's called a field in physics. And a field, simply put, in physics, is a function that has a value at all points in time and space. So for example, the temperature in this room is an example of it's called a scalar field. And if there is, say, a fireplace in the corner over there, and you wanted to figure out what the temperature in the room was, you could have a function that describes that, and of course the temperature would be higher near the stove, and it would get cooler as you went over into the opposite corner of the room. And so the function would be just a function where you would put in the position in the room and the time, and it would tell you what the temperature was at that point in space, at that point in time. So that's simply what a field is, and there's lots of examples. So a gravitational field is a field, or an electric field. And so it's a mathematical tool that we use as physicists to describe some type of quantity that has a value distributed throughout space. So another example would be the pressure in the air in the room. So whenever I speak, it makes sound waves, and you have these oscillating pressure fields that propagate out from where I'm speaking. And so that could also be described through a field by describing what the pressure was at every point in the room, and also how it's changing in time as the sound wave propagates out. So the wave function is a field. It's a more complicated field for various reasons. It's a vector field, and it's complex also. Complex as opposed to real. But in essence, it's a field, and that's enough to know for the time being. The strange thing about psi, let me back up. So psi is the field for a particular quantum particle. And it turns out that when you look around you, we see all kinds of different things in the world. There's an uncountable number of things that you can see and interact with, and none of them are the same. It turns out when you look at the universe at a very small length scale, essentially everything breaks down into just four components. You have protons and neutrons in the nuclei of atoms, you have electrons that fly around the atoms, and you have photons, which comprise light. And there's a few other exotic particles, neutrinos and muons and things like that, but neutrinos you never interact with. They just fly through the whole Earth and never do anything, so you don't really run into them on a daily basis. Well, you do, but they don't do anything, I guess. And muons you only produce typically if you mash things together really hard in some particle accelerator. As far as your experience every day, everything that you interact with is from these four components: protons, neutrons, electrons, and photons, which is important to know. And the wave function psi then would be a wave function that's describing one of these particles. And you can also have joint wave functions that describe several particles at once. For most of this talk, I'm going to use electrons as an example. for what we're talking about, just because it's a nice simple thing to talk about, nice simple example to use. So for most of this talk, let's just, in the back of your head, if you're like, wait, what are we talking about? Let's assume psi is the wave function of an electron. Yes?
So if we take your definition of a field, it means it's a function that expands over all of time and space, or all of space.
Yes, sir. And it can be 0 in many regions in space. So it doesn't have to have a value everywhere. It could be 0 everywhere except right here, maybe. But yeah, it has a value at all points in time and space.
That's very different than a particle model, a classical model.
It is.
Something is here and it stops at a certain place.
It's very different. I'm going to get into that in the interpretation section about sort of how that distinction between those two. Okay. Yes, sorry.
One last question. You keep using the word complex. You mean it mathematically, right?
I mean mathematically complex.
So
I may not be being
plan.
careful. I may sometimes just mean complicated. But in general, yeah, by complex I mean a combination of a real and imaginary number.
Okay, thank
Yeah. Catch me on that if I screw that up. So the first sort of philosophical conundrum that one runs into when they try to understand how quantum mechanics works is the question of what does psi really mean? So we know that psi is a field that's describing an electron, but what does it correspond to? And the unfortunate thing for those of us that like to understand what we're reading about is that it doesn't correspond to any physical quantity, as far as anybody knows, at least. Well, that seems strange, right? Well, yeah, it's not all bad, because when you square it, then you do get something. So when you square it, specifically the modulus squared, which gets into the complex thing, which don't worry about that for the time being. But essentially, when you square it, you get the probability density. So the wave function itself isn't necessarily related to any physical concept, but when you square the wave function, it gives you the probability density of finding the electron in some region. So I have here a graph of a wave function squared. So this means that the electron is most likely to be at this peak here, and it's less likely to be at the small areas of the tail. And if you added up the area under this curve in this blue shaded region, and divided that by the total area under this curve, looks like that's roughly maybe 2/3 or so, that would mean that you have a roughly 2/3 chance of finding the electron in that blue shaded region. So once you square it, then it's a pretty intuitive concept. It's okay, so the wave function is like how likely the electron is to be there. But it's important here that the wave function squared is not what goes into Schrodinger's equation. Schrodinger's equation deals specifically with the wave function itself. But the physical result you get out once you square it. I want to have just a really quick, brief discussion about the calculus that's on this slide, just to make sure everyone's on the same page. So there is a derivative here. We're taking a derivative of the wave function with respect to time. That simply means we're calculating how the wave function is changing in time. So it's the rate of change of the wave function. There's also this curly S thing, which is an integral, of course. This is a three-dimensional volume integral, but for the purposes of this talk, just all this you really need to know is that this means that we're adding up the area under some curve. We're adding up a contribution of some value over some region, and in this case, that gives us a total probability. Yes?
So we've got this field, the electron has a probability of being anywhere in that, but the electron itself is still a very small finite particle.
Right. Yes. Yeah, well, it's both, and neither.
If the wave function is a probability, or the square of the wave function is a probability.
It's the probability of finding the electron in that position. So when you actually perform a measurement on the electron to detect it, then it'll only ever be detected in one position.
The probability of the detector going off.
Right, yeah. And it does snap, which is the collapse of the wave function, which I'll get into later in a lot more detail.
Okay, just trying to understand the difference in scopes. I mean,
right,
essentially, this is going back 40 years, so I'm trying to...
Right, yeah. Yeah, when you measure it, it's only detected at a single point, and it's acting like a particle. However, when it's not being measured, when it's floating around doing its quantum thing, it acts as a wave and has very definite wave-like properties that follow. They're dictated by the wave function.
So you're saying that in the quantum realm, there's a linear probability of it being there or not. When the wave function collapses, it becomes binary and it's either there or not. Is that
this isn't a straight line, but...
Well, no, I mean linear in the sense of you can say there's a 50% probability of it being there. There's a 75% probability
yeah,
of it being
and
there.
then it snaps when you
and
actually
then it
detect
snaps to a binary from a linear thing.
Right, and that's the collapse of the wave function, which I will get into later in the talk. But and that's obviously a very important aspect of this, which I'll get Any questions, other questions so far? How are we done? Okay. So,
Is it better to, like, as opposed to saying that you'll find the electron, it's better to say that the probability that you'll get the wave function to collapse?
well, so the wave function collapses anytime you detect it, so anytime you measure it anywhere. But then whenever it is detected, it's always detected at a single point. For all anyone has been able to tell, the electron is a true point particle, meaning that it has no spatial extent whatsoever. So it's only ever detected in a single position. But in the interim, before you mess with it, and so the point here, of course, which we'll get into more later, I don't want to get too off track, but the act of observing something and measuring something is not by no means a passive process. That you can think that if you're just hanging out in your room and you see somebody walking down the street outside, that you're not messing with them and that you'll know that you're looking at them. But for much smaller things on a smaller length scale, the only way you're able to see anything is by bouncing light off of it or having it interact with something. So it requires some interaction with the electron which messes with it, which is ultimately what causes the wave function to collapse. So the act of measurement is a very active process, which causes this transition from the wave behavior to the particle behavior.
And the wave function collapses when you detect it, whether or not your answer is yes, it's there, or no, it's not there.
Well, no, it collapses when you actually detect it. So if you say looked here and you don't see it, that doesn't necessarily mean that you collapse its wave function. You could have, but you don't necessarily have. But
You alter it, because by then you've zeroed out the probability that it's there. Before you had a thing which had some probability of being there, and you've altered the probability distribution,
Right.
because
If
by
you look-
measuring it there, you've made at least sure that there it's zero.
yeah, good point. Yeah, so when you measure it, and if it's not there, then that does change the wave function, but doesn't necessarily collapse it to a point because you still don't know where it is. So, I know this is what your guys' questions, which are great. This is certainly focusing on a lot of the really interesting aspects of this, which I promise I'm going to get to. But I do want to sort of we're going from the ground up. We will get to that, I promise.
So I shouldn't ask you about quantum Bayesianism either, should I?
Not yet, at least. Okay, so we had Schrodinger's equation, and there's a lot going on. There's a lot to unpack here. We have this imaginary number, we have Planck's constant, we have this derivative, we have the Hamiltonian, and we have acting on the wave function again. This is a lot to unpack. There's a lot going on here. So what I'm going to do is break it down to a much simpler equation. We're going to start with just this equation here. I think I'm missing a few. Where are my other equations? It shows up there. Hey, well, okay, we'll do it this way. I don't know what's up with the magic disappearing equation. Okay, so we're going to simplify it down. We're going to first of all get rid of I and get rid of h bar. Also, this h is the Hamiltonian, which I'll explain later, but for now we're just going to assume that this is, instead of h, we're just going to have some random positive constant, which I'm going to call lambda. And instead of talking about the wave function psi, which doesn't mean anything physically, directly, we're going to talk about the population of bacteria in a petri dish. So my goal here is just to explain how this differential equation, which is much simpler, works and operates, so that we can then build on and get to the more complicated Schrodinger equation. So this equation here, this says that the rate of change of the population is equal to some positive constant times the population itself. And that governs the dynamic of Malthusian population growth, which is shown in this graph here. And if you think about it for a little bit, you can convince yourself that this makes sense. So what happens when you have bacteria that are reproducing? So say they have a steady supply of food, so they grow at a constant rate. And say you start off with 2 bacteria, and every minute the bacteria grow big enough to where they split into 2 more bacteria. And then once another minute passes, that happens again, and each of those bacteria is split into 2. So in that case, we could write out what is the population of bacteria as a function of time. So at 1 minute, we'll say that there's 2 of them. At 2 minutes, those each split, and we then have 4 bacteria. And then after 3 minutes, each of those 4 split, and we have 8 bacteria, and so on. Excuse me. I had too many Topo Chicos. So the point here is that as the population gets bigger, there's more bacteria to split in half, so the rate at which the population is growing also gets bigger. And that's what we see here, right? So as the population gets larger, the slope of this curve also gets sharper, and they grow more rapidly as you have more of them. So if we wanted to describe what this equation is generally for any time t, we would say the population as a function of t in this case is just equal to 2 to the t. Right? So we put in 1 for t, we'll get 2, put in 2, you get 2 squared, you get 4, and so on and so forth. So this is the solution to the example that I talked about in words. The general solution, or just a more convenient solution, is this form here, where we have another random constant a, which is just any constant, times this number e, which is Euler's constant, raised to the lambda times t power. So a couple things about this. First of all, why am I bringing up some random number e, which is shown here. It's an infinite, non-repeating transcendental number, which is 2.71828, and it goes on and on. Why am I doing that instead of 2? Well, the reason is that in this example I gave you, it's true that the more bacteria you have, the faster they grow. But it turns out if you work out how fast are they growing exactly at any given time, it turns out that they're actually growing a little bit slower than the population itself. It's proportional to it, but it's not equal to it. So if we take dp dt, it's actually natural log of 2 times 2 to the t. And natural log of 2 is, I think, 0.69 or so. So the rate of change of the growth, if you use 2 here, which makes sense of the example we gave, and it is exponential growth, but the rate of growth is not exactly equal to how many bacteria you have. It's actually 0.69 times that. And if you imagine increasing this number, say you had 3 to the t, say you had some type of bacteria where there's 3 of them, and every minute each of those 3 turn into 3 more. So this is kind of a weird biology, but just, you know, hypothetically speaking. In that case, your population would be equal to 3 to the t. And in this case, if you worked out how fast is the population growing, it's actually growing faster than the value of the number of the population at any given time. So it turns out that E is just the magic balancing number between 2 and 3, where the rate of growth of the population is exactly equal to the amount of the population itself. And I could easily spend an entire talk on E and, you know, why this might be the case, that this is the right number, that would get us way too off base. So just take my word for it for now. But e to the t is just the magic function where when you take d dt of it, you get exactly e to the t back. And the fact that that happens just makes it an extremely useful number to use when you're talking about these things, because you don't have to worry about what e to the t is going to do when you take a derivative. It just gives you the same function back. There's also this constant lambda out front. So if you think about what happens when you change lambda, say, you know, we had the example before where the bacteria split every minute. If you change that to where they're splitting every half of a minute, then they would obviously be growing twice as fast. And that is done in this equation by changing lambda. So that means that the rate is if you half the value of lambda, that would correspond to doubling the, if you half the value of the, sorry, I'm tying myself in knots. If you double the value of lambda, you're doubling the rate, which is effectively going from splitting every minute to splitting half of a minute. So that means that when you, so if you, this is gonna, I'm belaboring this point a little bit because it'll become important later. But when you take the derivative of e to the lambda t, see how fast is this changing? Of course, the derivative of just e to the t gives you e to the t back. When you take this derivative with t, you get a factor of lambda out front. So this scales, putting something up here in the exponent scales how fast it's actually growing. So you can make, you know, so increasing lambda means that it's growing faster by that factor. Okay, so that's population growth. What happens then if we...
That's an infamous time constant.
It is, it's very infamous. Troublemaker. Oh.
They are Ising equation.
Yeah. Okay, so what happens then if we throw a negative sign up there? All we're doing is we're taking the same equation, but we're adding a negative sign up front. Turns out that this describes radioactive decay. Mathematically, not a whole lot changes here. You have a negative sign up here, which just means that you carry that negative sign up into the exponent. So instead of a e to the lambda t, we have a e to the minus lambda t. Straightforward. But intuitively, this negative sign does a couple of different things. First of all, this means that since our population is positive, and we already said that we're choosing lambda to be a positive constant, that means that the rate of change of the population is always going to be negative. It's always going to be getting smaller. This is positive, so it'll be shrinking. This also means that as it shrinks, the value of P of t will get smaller. So that means that it will shrink more slowly as the population gets smaller. And you can see from this graph that that's what's described here. So it's starting out decaying at some certain rate, but as it gets slower, then the rate slows down and it shallows out and it doesn't decay as fast as it starts to decay. And this, for example, describes things such as carbon-14 dating uses this technique. So if you have a bunch of atoms of some radioactive type where they have a certain likelihood to decay every minute, once half of them decay, you only have half as many that can still decay, so they're not going to be decaying as fast because there's not as many of them there to decay. So it's sort of just the inverse of the bacteria growth example, where instead of the more you have, the faster they grow. Here, the fewer you have, the slower that they're able to go away, because they're going away at some certain rate. So it's real similar to the exponential growth, it's just flipped. And also, if you think about it, if you just flip this graph around the y-axis, you get back to the exponential growth curve. So it's also just simply changing the sign of the time, is also what this is doing. But I wanted to kind of explain a little bit some of the dynamics that determine how this works. Any questions about this one? Okay, pretty basic stuff so far. I hope everyone's with me so far. But now we're going to add the I back in, and this is where things get problematic. So I is the square root of -1, and we're going to put it back into this equation where it belongs. And so, of course, -1 doesn't have a square root, which is why it's called the imaginary number. But when you square I, you get -1. And you know, this is another thing that tends to often bother people when they first learn about this. They're like, what are these mathematicians doing? They're just making up things that don't exist. I'm like, what? When did they get a job? And it turns out that it's not, there is actually a fantastic reason for doing it. It's that even though I doesn't actually mean anything, it's extraordinarily useful for all kinds of things in math. It just makes everything work beautifully for fairly complicated reasons I probably won't get into. But I like to think of it, instead of worrying about the fact, okay, what is I really? Similar to the wave function, which also isn't anything really until you square it. I like to think of it as a sort of a placeholder. So you don't want to be negative yet, but you want to be able to have something that can be multiplied together and then get you to being negative. And it turns out that being able to do that mathematically just opens up so many doors as far as how easily you're able to calculate things. So one other effect of I, so I times I is -1. This means that if you divide through by I, that I is equal to negative of its inverse. It's also a strange property, right? So 2 is not equal to -1/2. That doesn't make sense. And no real number has this property, but I is negative of its own inverse because when you square it, you get -1. So, what happens to this equation when you put an I in here? It turns out that instead of getting exponential growth or decay, you get an oscillatory motion. You get, this is the solution shown down here. So, what do we do? So we have this I here, we're going to move it over to the right-hand side. So just divide through by I, so we get 1/I. This 1/I, as we said, is -I. So dx dt is -I omega x of t. Oh, by the way, sorry, let me back up this a second. I changed p and lambda on you to x and omega. Reason being that it makes more sense to have position oscillating than it makes sense to have a population oscillating. So I just changed x and omega functionally are both just, this is a function and a constant, but I changed it to a more intuitive example for what it's doing.
Come on, as biologists with predator-prey models would beg to.
Fair point. So once we have this equation here, so dx dt is -I omega x, mathematically the solution is very simple. We still just have some constant in front of x that's equal to the derivative, so we just put that constant up in the exponent and that's the solution, we're done. So it's just a, that's, a is our arbitrary constant that can be anything, e to the -I omega t. And this is sort of the magic confusing step, which again I could spend a whole talk on this, which I'm not going to, but this e to the -I omega t is equal to cosine omega t minus I sine omega t times a. And so when you exponentiate I, you get a sum of both a real and an imaginary component that both oscillate in time. And this is certainly a fascinating thing when you first learn about this, like exactly how does this all work out? It does. This graph here, by the way, so the black curve is our cosine, and then I'm showing in red the corresponding sine wave, so you can see what it looks like. I'm not going to get into too much of the weeds about why this works, but just very briefly, one way you can kind of wrap your head around this is that whenever you exponentiate things, if you have e to the x, say, write this one out. So if we have this e to the x, of course this grows really fast as x gets bigger, that's what exponential functions do. You can represent this as an infinite sum of powers of x, like so. And it goes on forever, and it has a bunch of infinitely more terms of polynomial powers. And I'm not going to explain why this is true, but it's just a Taylor expansion of it. Because of this, because it has all these higher powers of x, you can use that to understand why it grows so fast. Because you have, as you make x larger, you have this x to the 1,000,000th power that's in this expansion somewhere that's going to grow really fast. When you put this I up here, you see that we have a series of different powers of 1, 2, 3, 4, 5 that are part of this exponential function. Every even power of this expansion is going to have two factors of I that get multiplied together to give you a real number, which is going to alternate between being positive and negative. Every odd power in this expansion is going to give you a leftover single factor of I that will multiply by a bunch of even powers of I that will give you a real number. So you have an I left over, and that is where this cosine and this sine, I times sine come from. It's from those two different aspects of this expansion. If you think about what this expansion is doing, you have a bunch of terms that are all positive. They get really big as x gets big. And that's one way to understand why e to the x grows so fast, is because you have all these terms that are all adding up together to give you a large number. Once you put an I in here, then every time you square it an extra time, you get an extra negative sign, so that these terms here are not all positive. They alternate back and forth between being positive and negative, hence giving you a more complicated function that isn't strictly growing, it isn't strictly decaying, and hence you get some type of strange oscillatory behavior. That's all very hand-wavy, but hopefully that helps a little bit to sort of see where this comes from. There is, I think, a more clear way to explain it, which is on this slide, which is what happens if we take another derivative. So dx dt, of course, is just velocity. That's the rate of change of the position of something, say mass on a string. If we take a second derivative, that's the rate of change of the velocity, which is, of course, the acceleration. So on this graph here, the curvature of the graph is related to the acceleration of the particle, right? So that if here, sorry, and then here, this is, the x-axis is actually time here, and x is this way. So it's oscillating back and forth, and how much it's curving is related to how fast it's accelerating. So if you take a second derivative of this same differential equation, so, different equation now, but if we take a second derivative of x, so this is our function for x. When we take one derivative, remember we pull down whatever is up in the exponent, so we get a minus I omega. When we take the second one, we just get another factor of minus I omega. And when you square this, then these two negative signs cancel out. The I gets squared to give you a third negative sign, and you're left over with one overall negative sign, plus an omega squared up front. So this equation here, if you recall, looks very similar to our equation for exponential decay, except for exponential decay you had dx dt is minus some constant times x. Here we have two derivatives of x with respect to t give you minus a constant times x. And so what this means intuitively, for exponential decay you have the rate of change, the rate that the function is decreasing, is going to be lockstep in place with the amount that you have left. So as soon as you have half as much, it's going to be decreasing half as fast. Once you have half of that left, you're going to have, again, it being half as fast as it's decaying. So you have, exponential decay gives you sort of a Zeno's paradox in that you never actually get to zero. It just keeps having because the speed keeps slowing down as you don't have as much. And you never get to zero. For oscillatory motion, for this equation, since it's the acceleration that's negatively proportional to the amount that you have, that means that the amount, the degree to which it tries to change the velocity is negatively proportional to how much you have, which means that the actual velocity lags behind, in a sense, the acceleration, because the acceleration has to act on it for a while. It has to accelerate for some period of time before the velocity changes. So that the effect of oscillatory motion is that, so here you are at the top, and of course it's trying to bring it back to the bottom, so it's accelerating down the most because the x has a large value, which is positive, so that means the xt will have a large negative value. And it starts to bring it back down. But by the time it ramps up some speed, which has a delay to it before it's able to accelerate, it's already plummeting towards the center, and it's not able to stop when it gets there, so it flies through the center and then gets overextends and gets to the other side, where then the direction flips, and it then slows down at the bottom. Yes?
Are we matching this oscillatory motion into anything in the real world right now, or are we just working out the math of oscillatory motion?
Great question. Well, luckily I have this next slide. Yeah, so let's say that it's, and good point. So let's say it's a mass on a string, on a spring. So we all know when we have a mass on a spring, if you stretch it, it wants to pull it back. If you compress it, it wants to push back. So it wants to sit in some happy equilibrium. If you perturb it in either direction, it'll push against that. Of course, any real spring, you can stretch it enough where it breaks. We're assuming you're not stretching it too much where it doesn't break the spring. In that case, the restoring force on the mass is going to be negative some constant times the position, where x is measured from this equilibrium position. So to the right of that, x is positive, the force pulls it back. To the left of it, x is negative. The negatives cancel out and you get a positive force. As we know from Newton's second law, force is the mass times the acceleration, so mass is just a constant. So effectively, you can think of this acceleration is related to the force that's acting on it. And so in this case then, we have the acceleration, the amount that the mass is being accelerated is the strongest at either end. And so it starts to, when it's at, say it's over farthest on the right, then it'll be pulled back towards the middle and it gains up some speed, but it doesn't behave like exponential decay where it never gets there because, so saying the acceleration acts to change the velocity, but then the velocity doesn't change in time to stop at 0, if that makes any sense. For exponential decay, you have a case where the velocity directly changes as you reduce the position x. Here, the acceleration changes with x, which then has to act on it for some time to change the velocity, and so that's why it ends up overshooting, and it's infinitely trying to correct itself, but then it goes too far to the left, and it goes too far to the right, and it goes back and forth. Yep.
So just to make sure I understand this example, the wave likeness of your spring there is not mapping to our wave. What's the wave is actually, we should turn our spring this way so that it matches that wave going up and down?
Which wave are you talking about?
Okay,
The sine curve, I think you're getting confused by the wiggliness of the
Oh,
representation of
you're
the
right, I'm
spring.
sorry, yeah, this should be rotated 90
Right,
degrees.
that's what I'm saying,
Yeah.
yeah, and then it's the move along the x-axis is the movement through time, right?
Yes, yeah,
Okay.
yeah, thanks for clarifying.
So yeah, the wiggliness of the spring is just happenstance.
Yeah, you could imagine it being a rubber band.
Right, okay.
Right.
Just making sure, I thought that was the case.
Okay. So we're pretty far along. We're actually almost to Schrodinger's equation at this point. We haven't neglected h bar, and also capital H we've just said is a constant, which it's not. So we have a few more things to go. But so far, hopefully what's clear to everybody is that when you have a differential equation that has an I in it, and you're taking the time derivative and it's equal to something times the thing, that gives you oscillatory motion. It gives you some type of wave motion that's going to oscillate back and forth. The speed that it's oscillating back and forth is going to be proportional to this constant out front. So omega here is frequency. And similar to how having a larger lambda in the exponential case means that it grows or decays faster, here having a larger value of either h, if that was a constant, or this omega out front, that'll make it where it goes back and forth a lot more quickly. Okay, so h bar. Let's talk about that a little bit, this funny h with a slash through it. So that's Planck's constant, and its value is here. It's an empirical constant. So this is just something that has been measured by physicists by doing experiments. It's not related to any other fundamental constants as far as we know. This is something that's been measured in laboratories, and this is what it appears to be to some level of accuracy. It probably has a few more digits that they've worked out. It's very small, as you see, 10 to the minus 34. So mathematically, it doesn't do anything to this equation, right? So you have a really tiny constant here, but it's just a number. It's just a normal number. So it's not going to change any of these dynamics. What it does do is, for fairly complicated reasons, which I'm not going to get into, but it sets the scale at which quantum effects become apparent. So for example, of course, the quantum in quantum mechanics is referring to the fact that nature becomes quantized into individual photons and individual particles and individual discrete energy levels. And h bar sets the scale of that quantization. So for example, the energy of a single photon of light, which is the smallest unit of light, can be different depending on the frequency, but it's equal to this constant h bar times the frequency. So it sets the level at which light is no longer a continuum, wherein it then becomes discrete chunks of light, for example. And I don't want to spend too much time on h bar, but just it's of course a very fascinating constant, sort of the fundamental quantum mechanics constant, and it's tiny. And the fact that it's tiny is why you don't see quantum mechanics in your everyday life, why you don't run into it down the street, because it's so small. It's related to the fact that it only occurs on small length scales.
You could also just get rid of it by choosing the right units.
You can always just choose the right units. That's true.
I was going to ask about those units. That's seems odd.
Meters squared kilograms per second? Well, it's not like. So this is actually units of energy times time, which is the units of action, which is a whole another bag of worms. So we're gonna skip over that. It has strange units. You're correct. We'll just leave it at that for the time being. Okay, so the last piece of the puzzle, H is for Hamiltonian. We've been calling H just some random constant. It's not. It's actually what's called an operator, which is why I put this little hat over it. And here also, so this is the same Schrodinger's equation. I just put in explicitly that both the wave function psi and the Hamiltonian depend on three-dimensional space and on time. So this is just saying that psi is a field, right, as I was explaining earlier. And I guess technically you should always have this up front to show what it depends on, those, just so it doesn't clutter up the board too much. I haven't been including it. So here's H, and it's the energy of the system, or it's related to the energy of the system. It gives you the energy. And we have H next to psi, but it's an important thing to point out that H isn't simply multiplied by the wave function. It acts on the wave function in some more complicated manner. If the wave function has a definite energy, if it's in a state that has a definite energy, there's only one energy, in that case, that's called an eigenstate of the Hamiltonian, and in that case, H does just multiply it, and the number that multiplies by it is the energy. However, it can often be more complicated where there's some more complex interaction between H and psi that can even change the overall state, so you don't end up with the same state on both sides of this, and it gets a little more hairy. In linear algebra terms, one way to think about it is that H acts like a matrix and psi acts like a vector, so it's more of a matrix multiplication. Another way to understand this is that, so one component of the energy is the kinetic energy, which is the energy of the motion of the electron. It turns out, for reasons I'm not going to derive, that this is the form of the kinetic energy, which has a second derivative with respect to x. For 3 dimensions, there's also a corresponding y and z term. But so you can see here, if you have this in front of psi, it's going to be taking a derivative of psi. It's not just going to be multiplying it. So that's an example of how it's not just multiplying the two things together. They kind of interact in a more complex mathematical kind of way. But most of this I'm just sort of saying just as sort of a disclaimer. For the purposes of following this talk, it's enough to know that this characterizes the energy and it acts on the wave function and can give you the energy back. The energy generally has two components, the kinetic energy and the potential energy. So kinetic energy being the energy associated with the motion. The potential energy is the energy associated with all the other particles and forces that are acting on it. So if you're in a gravitational field like we are, then of course raising up an object raises its potential energy because you're going against the force. And if you go in the direction that gravity pulls you, that's lowering your potential energy. So V is the energy associated with the environment that you're in, which results ultimately from all the forces of the various things that are pushing and pulling on you. The one thing I want to say about the kinetic energy here is that, so we have that there's a negative sign here. That seems weird. Kinetic energy should be positive. That ends up going away because when you take these derivatives, you pull down a couple of i's, and that cancels out this negative sign. So kinetic energy is always positive. So this is not a real intuitive concept. The second derivative with respect to x, which is the curvature of the wave function along the x direction. And if you look at these two waves, so say these are both waves of light, and this one is going along at a pretty low frequency, this one's going along at a high frequency. Of course, the high frequency one has a much higher energy. And if you look at this, you can see how it also has a much higher curvature because it's curving back and forth a lot more rapidly. So I'm not gonna derive where all this comes from. That would get just too far afield. But at least you can sort of see that, okay, so if you take this thing, if it's more curvy, the wave function, then that means it'll be a higher energy light wave because it's doing more stuff. And so more curvature in the wave function leads to a higher kinetic energy.
These are your bleeding concepts.
I'm sorry?
Your bleeding concepts, at least in my head.
Which ones?
So you've got the wave function, which is just a field that we can only square to get a probability out. And you're applying an operator to it, the Hamiltonian, and you're talking about where is the energy. It's only in the Hamiltonian, right?
So yeah, the Hamiltonian acts on the wave function and can give you then the energy back out. So if this is if this has a definite energy, then once you work this out, you'll end up with the energy times psi at the end of the day. So it does give you the energy. But the thing is that psi can actually have multiple energies at the same time because it can be in superpositions of different waves, which I'll explain in a little bit. In which case, it doesn't just give you a single energy back, it's a little more complicated. I don't know if that answers your
It
question.
helped. It helped.
Okay.
Thank you.
How you guys doing? Following along? Okay. Okay, so what I'm going to do now, so we're actually done, by the way, so let me take a breath a little bit, appreciate what we figured out. We're done, not with the talk, but done with getting through Schrodinger's equation. So we built it all back up now. So Schrodinger's equation is an equation that describes how the wave function behaves. And so what it says is that, so the wave function is going to be a wave that's oscillating. And it's going to be oscillating more if the wave function has more energy. So it'll be oscillating more rapidly, have more curvature in that case. And so generally this equation just says, based on what the energy is, you can relate that to how it's changing in time. And roughly the more energy, the more it changes in time, the more rapidly. Yeah.
Why is there a hat on the H in the Schrodinger question? In the top equation, you've got a hat on the caret on the H, and
Yeah, why isn't it here?
Yeah.
That's because I'm lazy.
okay. So
Here
it is the same H. It's not like some.
Yeah, sorry, same age. Although it actually shouldn't be here because so the actual energy that you get out is not an operator; that's a scalar. But the same age for the purposes of this talk. That's just me being nice.
Okay, so that's just going the energy operator is the energy value.
Yep.
Okay. But then the K down in the bottom line should have a hat because
It
that's
sh-
the operator.
It should. Yep.
Okay.
That's,
Okay.
That was my oversight. Okay, so I'm now going to apply the Schrodinger equation to a couple specific examples to explain how it actually works in practice. So the most straightforward case, in a sense, is the free particle, which means that you have no potential energy, it's just flying around in space. So the only energy that we have to deal with is this kinetic energy here.
So that's a free particle in a vacuum?
Yeah, in a vacuum.
Okay, not, because it's gotta be a vacuum, it can't just be in space for this to work.
Well, then it's not free.
That's not free, by definition, yeah.
Yeah, space is not free. There's things in it. So I'm not going to drive this wave equation, but the solution to Schrodinger's equation, if you set v equal to 0, turns out to be this. And this is a wave in both time and space. So we have this, remember our e to the I something is a wave, that's a sinusoidal behavior. And here we have e to the I, the wave, some wave vector times position, and then also e to the I, the frequency times time. And so if you look at this plot here, first of all, if you freeze x at one particular value and just follow what's happening at that point as time evolves, you see that this black dot in the middle follows the sinusoidal pattern in time up and down. So that's a wave, a sinusoidal wave. Additionally, if you froze this animation in time and looked at what the wave function looks like in space, you'll see that it is also a wave in space. And so that's what this equation is showing. And this describes a traveling wave, which as you can see, it looks like it's traveling to the right. So the solution in the free particle case turns out that it's a wave in time and also a wave in space, and that leads to a traveling wave. And so, for example, this is the wave function that describes the light leaving this laser pointer. It's just a wave that's propagating out that way, and it's a sinusoidal pattern in both time and space. Light is also a vector, and there's electric and magnetic fields involved, so it's a little more complicated, but essentially it's a wave function of this form.
Can you define the y-axis?
Yeah. X, Y, Z. It's just the perpendicular one to X. Oh, you mean on the graph?
Yeah.
Oh, yeah, sorry. Yeah, thanks. I've actually been really sloppy about this. I hope this hasn't been confusing. The wave function is the y-axis, which I have been a little cavalier about changing that. Here also the y-axis is the wave function, but before when we were talking about our spring, the y-axis was the position. So I have changed that a little bit, and here the x-axis is time, whereas here the x-axis is space. So sorry, I'll try to be more careful about that. I know that's confusing. I've been switching it up a little bit. Good catch.
I guess I'm not 100% sure what you mean when you say the y-axis is the wave function.
So the value of the wave function, psi, is the height of this blue curve above the middle.
Well, yeah, but you're just saying the height of the wave is defined by how we define the height of the wave, if you say it that way.
No, I just mean that this direction, so the height of this blue curve is the value of the wave function at any given point. So this is x.
It's one of the components of phi because it's complex, so it's the real power of phi. Or
Sure.
phi,
Yeah.
phi,
Right.
psi.
Yeah.
The real power of psi.
Yes, right. So if you, maybe this would be less confusing if it wasn't moving. So let's look at this. So here, this is the wave function, this axis. This is x. So what this is showing then is that the wave function at this particular value of x is equal to this 1 in this case. And this isn't necessarily a normalized wave function, but we won't worry about that right now. So the y-axis is just the value
It
of...
sounds to me like you're saying we measure the y value of the wave on the y value measurer for the wave.
Maybe, let me explain maybe more physically what this means. So if you square this function, you'll get a similar function that's going to be all positive, but you'll have bumps like this, right, if you square it. In that case, the height of the bump would tell you how likely you are to find the electron at that position.
That's what I wanted. So it's probability.
Once you square it. But remember, we're dealing with size, not until you square it that you
I
get
see.
probability.
But
And you have the imaginary component as well.
And there's also the imaginary component, so I'm oversimplifying it a little
But
bit.
this is how we work out the probability.
Right.
Is what you're saying.
Yeah.
Okay.
Uh-huh.
That's what I wanted.
Yeah, so the height of this curve is related to how likely you are to find it. Okay, next example is the famous infinite square well. So here we're going to trap an electron or some quantum particle in a well where when it's confined inside the white area, there's no forces acting on it, it's just free inside there. However, at the boundaries, we have an infinite potential energy so that it's not allowed whatsoever to leave the well. It's trapped inside of it. Practically speaking, of course, you're not going to actually have an infinite potential energy, but you can very easily in the lab have it confined well enough to where it's effectively, so it looks pretty similar to being infinite. So if you then solve the Schrodinger equation to see what types of waves are able to exist inside of this well, you get these various standing waves, various harmonics of standing waves that can exist inside of the well. And they follow this pattern here. And an important thing about this, so when you solve Schrodinger's equation for this situation, you get a very important thing happens wherein the different types of wave functions that can exist in this environment become discrete. The wave function can't do whatever it wants here. It can vibrate this way, it can vibrate this way, but it can't vibrate sort of halfway in between those two rates. It's restricted to a discrete set of possible energy levels. And this is very closely related to what happens on a guitar string or on any stringed instrument. So if you have a guitar and you pluck it, then of course the string will vibrate back and forth. And if you have a really high-speed camera to look at what the string is doing, it'll look very much like this first animation here. Of course, that's a little exaggerated, it's not vibrating that much. But if you reduce this amplitude, that's effectively exactly what your guitar string will be doing, going back and forth. If you then touch the guitar string halfway down the neck, which is at the 12th fret, and then pluck it, you'll get the first harmonic of the string, which looks like this, where it's oscillating back and forth, but not in the middle. And that'll oscillate at twice the speed, so it sounds like an octave if you do this. If you do a harmonic, it's a double the pitch. And similarly, you can keep going, so if you touch the string a third the way down, then you'll get the second harmonic, which is again a higher frequency than the root by a factor of 3. And this is at the 7th fret. And then this one, if you touch it at the 5th fret, that's a quarter of the way down the string, and you get another higher pitch. And you can keep going down this row. There's various higher ones you can do. And so the cool thing about this, I think, is that, so this is, you can understand how this works just from a simple string that's taught, and by how that can behave depending on how you pluck it and then where you restrict it from moving. You can excite different types of oscillations of the wave, of the string.
But if you clamp the string down, then you're not really getting a harmonic. You're just shortening the string effectively, and so you're still getting the first harmonic just of a shorter string.
So if you touch it just in the middle and pluck it, it will vibrate on both sides because you're not holding it down here. So it does look like this.
So you're actually blocking the transfer of energy from one part to the other.
Right, yeah.
Gotcha.
But if you did hold half the string up till half and then pluck it, that would also give you the same pitch, but it's just effectively just shortening the string in that case. But it's similar, the same shape of the wave. So the cool thing here, I think, is that quantum mechanics seems very mysterious and crazy in what's going on, but what the wave function actually looks like in this situation is exactly analogous to how a guitar string is able to vibrate on a string, based on how much energy the string has as it's vibrating. And the higher modes of vibration then have higher energy, just like the higher harmonics have a higher pitch when you excite them. This can then be generalized to 2 dimensions, so if you think of this as a drum head, if you lightly tap the middle of the drum head, it'll vibrate much like this. But if you hit it harder, or if you try to maybe restrict it from not moving on these intermediate areas so that you can excite this higher excitation mode. You can have it make this more complicated oscillation where it goes back and forth like this. And typically, any real instrument that you play, your voice if you're singing or your guitar or anything, typically there's many contributions to the tone from a lot of these different normal modes. There's overtones and harmonics that are present in any sound wave typically. I mean, you can make a pure tone with a computer, but any real instrument, if you hit a drum for example, typically it'll have a large component of this primary oscillation, and it'll also have other ways that it's moving which are maybe not as strong, but it'll have overtones related to these higher excitation modes. And the reason I bring this up is that that's the same case with the wave function. It's also able to exist in a superposition of different types of vibrations at the same time, in the same way that a guitar string can vibrate in a more complicated pattern and have overtones and harmonics. So that you play a trumpet, say, and there's the primary tone that you're making, but there's also various other tones which are present in the wave. If you decompose it, if you look at what the wave is actually doing, it'll have elements of these higher harmonics present in it. Any questions about that? So this is what the wave function looks like in an infinite square well. We're going to now move on to one more example, which I think is maybe the most interesting, for me at least, of these, which is the hydrogen atom. So for hydrogen, you have a single proton in the middle, and you have your electron that's flying around it. Of course, they're oppositely charged, so the electron is attracted to the proton, and the potential energy has this form. So K is some constant, the Coulomb constant. E here is now the electron charge. There's two charges, so which is y squared. It's negative because it's attractive, and then R is the separation between the proton and the electron. So if you graph this, it looks like this, or this is a sort of a 2D plot of it, so that it's attracted towards the middle, where the proton is, and so the electron is going to hang out around that proton. And if you solve Schrodinger's equation for this case, of course the math is a little more hairy here, but the principles are the same. You just have this type of energy environment, which is sort of similar in a sense to the infinite square well. It's not exactly the same, but it's still, assuming the electron doesn't have enough energy to fly away and escape from the proton, it's going to be hanging around in that vicinity because it's attracted to it. So it's confining the electron in some region. And the solutions to the Schrodinger equation, in this case, give you all of the various electron orbitals. If anyone's taken a chemistry class, you know about s, p, and d orbitals, and there's also different values of n, the quantum number, the different energy levels of the wave function. So the primary one is just very analogous to the lowest mode of vibration on the standing wave, in that it's just a spherically symmetric wave that's oscillating around the point that it's attracted to. And similar to the drumhead with the more complicated motion, you can excite higher order oscillations of the electron around the proton, and you get these interesting dumbbell shapes, which are what you use, in covalent bonding and pi bonding in chemistry. And then if you excite the electron even more, you can have much more complicated shapes of how the wave function is oscillating around the proton, and these are purely analogous to the standing waves before, in that it's just a higher form of oscillation that gets a more complicated geometry because it's oscillating with more angular momentum in this case. But these are all just standing waves of a particular shape that comes out just from the fact that you have a central attracting point in a three-dimensional space. So when I first really understood this really blew me away for a while. Because I took chemistry in college, and I remember learning about, okay, you have these p orbitals and you can put them together, and then that's how you get bonding. But no one really explained why they're shaped the way they are. Why are they dumbbells? Why are there three of them? And I just thought it was really neat how this comes out just from the geometry of space and the fact that you're attracted. It's just the way that you can have a standing wave, a sort of standing wave that's attracted to some central point. These are the different ways that it's able to vibrate in that environment, similar to how the infinite square well restricts you to certain types of oscillations. Being attracted to a proton and being in this region around that also restricts you to certain types of oscillations that you can have in this standing wave.
So, but that potential energy doesn't look like it's particularly quantized.
The energy is not quantized. So the reason these are quantized is the same as the reason that the energy levels are quantized for the infinite square well, which is that anytime you have a potential energy that confines the electron to a finite region, that is what quantizes the energy levels. So before we had the free particle, the free photon, say, that's traveling, which is a traveling wave, in that case, the frequency can be whatever it wants. It's a continuum. You can have any energy that you like. There's no limit to what types of frequencies of light you can have if it's traveling. But anytime you have a wave function that's confined to a region, some finite region, that gives you a discrete set of different allowed vibratory modes.
And those are like the eigenmodes of the geometry.
Right, so you have a discrete spectrum versus a continuous spectrum.
Right.
So, because in the free particle case, you also have eigenmodes, but it's just a continuous variable k, say, or omega. Versus in this case, because, and it's a direct result of the fact that it's confined to a finite region. When you confine a particle, that gives you a discrete spectrum of only certain allowed vibrations. And it's maybe a little harder to see why that's the case for the hydrogen atom, but if you go back to this one, it's a little more intuitive. So at the ends of the string, you're not letting it vibrate there. These are just the ways that it can vibrate back and forth in a coherent sinusoidal manner, given that it's restricted at the two ends. You have to have some integer fraction of a wavelength in order to have it where the wave becomes zero at both ends of it.
Well, your discs actually show a better story for you.
Yeah. You have a question?
Yeah, on the other slide, if you say take a look at, say, the p orbitals now, presumably the p orbitals can actually be oriented in any oblique direction as well.
Yeah.
And presumably those should somehow be linear combinations. Presumably the three that are aligned with the axes are somehow a basis. But it doesn't look like any linear combination of those three would give you something that's the same shape but oblique.
So it's yeah. I see which it's a good question. I would say that the fact that we drew this line here is what's really is the arbitrary thing, right?
Right.
So I mean, you can draw your axes however you want, and
Yeah.
the point is just that once you have all three of them, they have to their relative angles
Right.
have to be at 90 degrees in order to have a
but
coherent
you can
oscillation.
have one that's somehow there are three that are independent. You can have the oblique ones which are not independent, which are somehow linear combinations, but presumably some kind of imaginary numbers game's got to be going into the fact that you can combine the three orthogonal ones to get oblique ones, because normally in sort of normal, if you're doing any kind of normal real math, there's no way that a linear combinations of those three gives you something that's oblique. It would give you something that's just a smudge of the two of those going in.
Yeah. So the reason they come out this way is just that if you it's mathematically when you work out the calculus for deriving these shapes, it's much easier to do it when you divide out the different coordinates and treat them and separate them. And so to get an oblique wave function of this form, you could easily just shift your definition of the axis, and thereby you have one. So those are also solutions to the wave equation.
Right.
But I think the main thing is just that to describe this at some oblique angle would give you it's a very ugly function, which would be really hard to describe in a, these are of course the what are the polynomials called? Forget. The harmonics, spherical harmonics, there we go. Which have a nice simple form in terms of the theta and the phi angle. If you wanted to describe this at an angle, even just having an equation to say what that is a very ugly expression, which you could probably do. I haven't tried. But if you did, that would still be allowed. I think it's just that, practically speaking, trying to describe it in some obtuse manner with the angles off just makes everyone's life a lot more difficult, so you don't usually do that.
I was thinking of something actually. I was just thinking, if you think of it as linear algebra, I thought that somehow that there are somehow three basis solutions, and the rest are somehow a linear combination of those three basis solutions. But then you'd have to have a funny concept of linear combination in order to take those three in and get something out that's oblique.
Yeah, I think you can do that. I haven't tried them. I think you should be able to, just because that would also be a solution, and there's no reason why you shouldn't be able to express it as a combination.
So I'm trying to understand the difference in the orbitals, and the s orbital is a lower energy state, so it means it stays in the potential well.
For a given value of n, it is. You can actually have, so if in your periodic table you have as you go down each row you have larger values of n, which they all still have an s orbital.
Right.
So there are about s orbitals that are larger than lower n values of p orbitals, but for a given level, yeah.
Yeah, let's just stick with hydrogen.
Well, no, even for hydrogen they have.
Well, yeah,
yeah.
we'll get way up there, yeah,
Yeah.
that's what the twos and two P's and all of that are. So the lower level the s orbital, first level, seems to me is it's a very low energy state. The electron is close to the proton.
Uh-huh.
And what that means, if you go back to your drumhead example, it means the area of extent is very low, or the radius of
Yep.
extent is very low. So I'm just trying to pull these together.
Yeah, yeah, sure.
So now when we go into 3 space, away from the drumhead model, okay, we now have a sphere. When we look at the drumhead, we had a couple of different modes that had different oscillations and that were orthogonal to each other.
Uh-huh.
And so these p orbitals are basically becoming those kinds of 3 space oscillations of the drumhead.
Yeah, exactly.
In this vague model.
Uh-huh, yeah, that's great.
All right.
One other thing I would add to that, so this is a graph of just the radial component of these different wave functions. And so as you said, you can see here, 1s is much closer to the nucleus. And as you get to 2s, which is a similar type, it's hardly present at all near where this one is large, and it's mostly concentrated at this larger radius. So they become sort of annulus-like as they get to larger levels, where they're mostly present in some band around the nucleus, not closer in. So I
was going to say something to point out is that the SP and D are the angular momentum values, right? So the 1s and the 2s that he's got on the graph there are different energies, but the same angular momentum, whereas you could, presumably have the same energy with an s or p orbital, but they have different angular momentum.
Right, so these shapes come about from the electron having more momentum going around the orbital, whereas the s orbital is spherically symmetric, so it doesn't have any net motion, in a sense, in some particular direction.
But the shapes of the orbitals, all I was going to say is, the shapes of the orbitals are just spherical versions of the exact same shape of what you have going on in a flat plane, well, an oscillating plane on the drum head, and a line on the guitar string.
They're different shapes. It's an analogy, but it's, the principle is the same, but they are different shapes because the energy is different, right? So the fact that this, so for the infinite square
You
well,
mean
remember
the well
there's,
is different.
the well is different.
And that's what gives us different energy shapes, but
Yeah.
the concept is the same.
The concept is the same.
Right.
But you have no energy and then infinite just to confine it for the infinite square well. Here you have a decreasing energy that's attracting it to the middle.
Right.
So it's a different type of, it's a different shape, but it's the same principle.
Right.
So has someone done an example, I'm sure they have, of just a 2-dimensional hydrogen atom? In other words, where we're going to constrain the...
Yeah, so graphene is a great example of the true two-dimensional physical substance. If you have a single sheet of graphene, then it has, and that's a huge active area of research, because it has a lot of really fascinating conductive properties, how electrons are able to act in a two-dimensional flat world.
Right.
And the electron wave function does still extend to some degree in that direction, but the larger motions are two-dimensional at least.
Yeah, I was just thinking more of a Godolphin experiment. What happens if the electron was constrained to a plane around the proton?
Mhm.
What would the shells look like?
Right, yeah. No,
Okay.
someone probably has done that, but I don't know what they look like off the top of my head. There might be some complicated technical problems that come about, but I'm not sure. But yeah, interesting point. So the other thing I wanted to just point out, which I've sort of touched on this in some of the previous slides, is that you can combine wave functions for a given electron. So the electron doesn't have to be in just a single orbital. As you probably, to chemistry, you may remember hybrid orbitals, where you can have a hybridization of s and p orbitals to give you some combination, which is just literally adding up those different vibrational modes together, similar to the way that a string can vibrate with a combination of different normal modes at play. So a quantum particle can be in a combination of many different states at a given time, which is called quantum superposition. And it's similar to a standing wave on a string where you have overtones and harmonics. And relating back the Schrodinger equation, so if 2 or more states both satisfy the Schrodinger equation, then the electron wave function can be in a superposition of those states. So in general, the Schrodinger equation can have a lot of different solutions, different forms of the wave function that can satisfy that equation. And in general, an electron can be in any combination of those at the same time. It doesn't have to be in a single one. Okay, quick recap. So here is our beloved Schrodinger equation. Hopefully this makes a little more sense how this works now. It's just a wave equation. It's describing a wave function that oscillates. And the way that it oscillates is related to the energy that's acting on it. So depending on the energy environment and also depending on its own kinetic energy, it can determine how the wave function behaves. The main takeaway points are that the wave function psi has no direct physical significance, which is why it's confusing, but once you square it, you get the probability of finding it. Schrodinger's equation describes what kind of wave functions can exist in a particular energy environment. So if you're in a square well, or if you have a proton you're attracted to, or various things, you can, for that situation, you can work out what the wave functions are. And there are actually a very small number of energy environments where you can do this exactly. For the most part, you have to resort to approximations because the math gets too complicated. And finally, for a given H, there's many different energy states, vibrational modes that it can exist in, and the wave function can be in some combination of those. Also, very importantly, for any time it's confined, that's when you get discrete, different quantized levels. It's the quantum mechanics. Okay, so that's the first part of my talk, which I think probably lasted a little while. So we're gonna not spend too much time on the rest of this, but I wanted to talk a little bit about some of these questions that came up earlier as far as the collapse of the wave function, what this means, and what philosophically what quantum mechanics is really saying in a more intuitive sense. So we've so far strictly been talking about the wave function as a wave, as a distributed quantity that exists over some region of space. However, whenever you observe the particle, as you astutely have noticed, it collapses to a single point, so it looks much more like this, which this is described mathematically as a delta function. So this is strange because the wave function, a wave, so the sine wave, for example, is distributed throughout space, and the wave function is defined to actually have, the sine wave is defined to have some value throughout all of space. Whereas the delta function, or this point particle, is 0 everywhere, but infinite only at this one single point in space. And these two things are actually precise mathematical objects, in a sense. They're Fourier transforms of each other. And this one has a definite position, but no discernible wavelength. And this one has a definite wavelength, which can be related to momentum, but no discernible position, which kind of leads back to the uncertainty principle. Hey, you don't know x and p at the same time. In any case, so whenever you observe a particle, it by some apparatus, it detects where it is, then it's only ever detected in one spot. Whereas most of the time, if you're not messing with it, it'll instead act in a distributed manner where it exists over some region of space. And that's a very counterintuitive aspect of quantum mechanics. One comment I want to make about this is that we have here an electron, which is a single ontological concept, right? So the electron is a single thing that supposedly exists in the world. And in describing it, we're using two mathematical constructs which are precisely opposite from one another, completely different, to describe the same thing. So I think to some extent, some of these counterintuitive aspects of uncertainty and teleportation in quantum mechanics, I think to some degree we should maybe expect some of that, given that we're using two contradictory concepts to describe the same thing. And I don't mean this to be too critical of quantum physicists and the people that came up with all this. So it works brilliantly for all kinds of applications, and it is certainly the best that we have as far as a description of the microscopic world. But at the same time, it's good to keep in mind that we're using two completely opposite ideas to describe the same thing. So you should maybe expect a little bit of weird behavior to come out of that, which is what we see. So a little more about the collapse of the wave function. An electron acts in many respects as a wave, distributed throughout space. However, when it interacts with a detector, it only ever interacts with a single localized detector. You'll never find two half electrons interacting with two detectors, or you'll never find a distributed electron stuff that is detected by some continuous detector. For example, as if you splashed, water in a pool, and you had a wall that detected the height of the water, you can detect a distributed wave that interacts with the wall. It's not the case for electrons. They're only ever detected at one specific spot in their whole chunkiness. And that's called the collapse of the wave function. One way to describe this is that before you observe it, the electron is in a superposition of many different states in some particular basis. And when you observe it, it collapses to only be in the one particular state that corresponds to the result of the measurement that you made. It's one way to look at that. That does require your basis that you're describing the wave function in to be in the same basis as the measurement. If that doesn't make sense, then just pretend I didn't say that. So the double slit experiment, for some of you guys may be familiar with, since it's getting a little late, I don't want to give the full-blown explanation of how this works. But it's a good example of of this particle wave duality in that, so the idea here is you have an electron gun shooting a bunch of electrons at the screen, there's two little slits in it, and if the electron acted like a bunch of pellets or baseballs, you would expect to find two probability distributions roughly lined up behind where these holes are. What you actually see if you construct the holes in the right position is you get this more complicated interference pattern, like this. And this makes perfect sense if the electron is a wave. So I like this picture here. So this guy has two sources of water waves, and he's vibrating the water at the same rate in both of these. And you can see these two circular wavefronts propagating outwards, but they interfere with each other. And at some angles, they'll interfere in just the right way where they cancel each other out, and that's why you get these flat rays coming out from it. So this is a very classical explanation of how this could work, and it makes perfect sense that they're waves. However, the weird thing is that whenever you observe with a detector where the electron hits, it only hits one spot. And you can slow this electron gun down enough to where only one electron's coming out at a time, and you'll still get this interference pattern in the accumulation of where all the electrons end up going. So what that means is that each electron does indeed go through both slits, because it's a wave at that point. But then when it gets detected by a detector, it snaps down to be only at one particular location. So,
Can I ask a question?
sure.
So, I've been looking a little bit at this stuff that people, it's like hydrodynamics and silicon particles bouncing on water and stuff. And so, if you've got, a lot of point phenomena, like particles or things bouncing, and then you're going to measure the sum of all those over time and accumulate them and get a distribution, how does that prove that it's a wave here? Because it seems like if it's maybe ergodicity comes into account here or something, where like, the chance of measuring something at one point in one place, if it's an ergodic system, then the distribution should be the same as like the probability of measuring it at one time.
I actually don't remember what ergodic means, but but I will say that this interference pattern, there's no way to explain why you should get there unless the electron does in some way go through both of these slits, which means that it has to be distributed in space, which means that it has a wave-like property.
Right.
Something has to be distributed in space.
Something has to be distributed in space, right? And there are non-local hidden variable theories that try to address this in a more coherent ontology. But
We can just believe in the average interpretation and say that the wave actually never collapses.
right, there's also that. There's many interpretations. So I don't want to keep you guys too long. So I guess a couple more things to wrap up with. I know it's getting a little late. So first of all, there's some pop science that gets a little sensationalized, which is ridiculous. So I just think it's important to mention this off before I close. That people say that, oh well, the reason that the wave function collapses is because there's some conscious observer that knows about it, and so it's like with the tree falling in the forest and nobody's there, then it won't happen. But as long as you know that it's there, then that means it happens. So that's just wrong. It's not how it works. It has nothing to do with whether anybody is conscious or not conscious. This is physics. It's not psychology. So there is no effect whatsoever of the consciousness or lack thereof of anybody involved in the measurement.
Ask the quantum Bayesian, they'll disagree.
That is their prerogative. That also relates to Schrodinger's cat, of course. You can't finish a talk on Schrodinger's equation without talking about his cat. The idea being here that you have some superposition of two different quantum states in this box here. And depending on each of those two different states, one of those states corresponds to a situation where it'll trigger this little hammer to fall and break this poison and kill this cat that's trapped in the box. The other potential state that it's in superposition of would not do that. And so remember how you can be in two different vibratory modes. You can imagine a situation where one of those vibratory modes could lead to a result of a measurement that will cause this to happen. The other vibratory mode will not do that. And so then and this was really meant as sort of a tongue-in-cheek example by Schrodinger, that would mean that if you don't look in the box, then this cat is both in a superposition of being alive and dead at the same time. Which clearly he's not. The reason being is what actually causes the wave function to collapse. This is the last thing I really wanted to talk about. Is that, so you have your coherent wave function, it's in some superposition. When you interact with it with a measurement device, you have a classical apparatus that you're using to try to detect what is going on there, and that requires interacting with it. And to get back to what I started with about thermal fluctuations, you have some thermally chaotic measurement apparatus that's interacting with your coherent quantum wave function. And by the time you're able to have any observable result from your experiment, there's a whole chain of randomly fluctuating particles and that are required to get this chain of communication out to where you can observe it. And throughout all that, the quantum coherence is lost and it's picked a single state or the other state, so that the cat's either alive or dead, for example. So the important thing to point out here is that the collapse of the wave function is inherently tied to the interaction of a coherent quantum state with a measuring apparatus, and that measuring apparatus is necessarily not a coherent quantum state. So if you wanted to make your measurement apparatus somehow some coherent quantum state, that would require a larger control measurement apparatus to do that with your measurement apparatus, and there's sort of this unending bootstrapping issue. So think about it this way. So you want to figure out the state of an electron, and so to do that, you're going to have some apparatus that's going to measure it. But you don't know exactly what the state of your measurement apparatus is. You'd have to have some larger measurement apparatus to measure what that intermediate apparatus was at. And this isn't much of an issue in the classical world, right? So if you're hitting a baseball, it doesn't really matter if you are off by a micron on where the baseball is. You can just use a ruler or whatever and take a video. But when you're talking about really, really small things, this becomes a much bigger fundamental issue about how to just the bootstrapping issue of how do you know what the state is of the thing that you're using to determine the state of something else. And I think that gets to the fundamental root of why there's a lot of these counterintuitive aspects to quantum mechanics. So sort of to say that a different way, I think there's a fundamental distinction between first elements that you're seeking to control and measure in any given experiment, and second elements that you're using to control the first elements. And our natural prejudice when we describe physics is we would like to think of the universe as composed of one type of thing. There's one universe, and it's composed of a bunch of stuff, and it has laws and behaviors that govern it. And that's the same regardless of whether it's the observer or the observee. And I think that's a mistake in a way. Not that there's not a lot of great things that physics is able to describe, but I think it's not entirely correct, I guess. Because the act of performing a measurement is so fundamental to how we're ever able to interact with the world in any experimental manner, I think it might be desirable to reconstruct physics to reflect this distinction, where there is built into the theory a distinction between the aspects of reality that you are observing and controlling and those that you're using to observe and control. And this is all a little hand-wavy and qualitative. I don't have this, I haven't written a paper on this or anything. It's just sort of my thoughts thinking about it. But as you get to smaller and smaller length scales, this becomes a bigger and bigger problem because you're requiring larger and larger precision in your measurements, so that finally, the fact that you don't know exactly what your device is doing, that your measurement device, eventually that will become an issue and it'll come back to bite you, which I think is, intuitively, that's at least how I've come to rationalize where the uncertainty principle comes from. And if that is true, then perhaps it's possible to express this fundamental constant h bar in terms of shortcomings of our perspective and of this prejudice where we're sort of inherently ignoring some of the uncertainty.
So you're a quantum Bayesian. You believe in priors. Prejudice is a prior.
What's a prior?
A prior is part of Bayesian probability theory, which is basically your beliefs of the system change the system, change your interpretation of the data. And so fundamentally, your prejudice that you're talking about there is your model of the system. And the collapse of the wave function is the change in your belief of the system.
We should bring this up over some beers.
Okay.
So that's it. Sorry keeping you guys. Thanks so much for your attention.